Hello, this is the second presentation in a series of lectures that discusses the direct stiffness method. In the first presentation, we talked about the formulation for a truss element stiffness matrix. In this presentation, we're going to discuss how to take those element stiffness matrices and assemble a global stiffness matrix, and then solve for the free displacements in the structure. Let's get started. We learned in the first presentation on the direct stiffness method that the method basically revolves around a structure or global stiffness matrix K, displacement vector delta, and a vector of externally applied loads P. In general, the goal of the direct stiffness method, after we develop the stiffness matrix and the load matrix, is to solve for the nodal displacements delta. Ultimately, the overall goal is to develop a set of simultaneous equations that can be solved by the computer for the nodal displacements. In the first presentation, we spent most of the time developing element stiffness matrices for truss members. Our next step is to take those element stiffness matrices and assemble them into a global stiffness matrix for the entire structure. It would be convenient if we could simply add the element stiffness matrices together to form the global stiffness matrix, but that simply isn't possible. First of all, the truss element stiffness matrices are only 4x4 matrices, and since our structure has 10 degrees of freedom, we know that the global stiffness matrix must be a 10x10 matrix. Therefore, adding the element stiffness matrices together in their current form fundamentally wouldn't result in a global matrix of the proper rank. Secondly, if we were to simply add the truss element stiffness matrices together now, we would be adding stiffness coefficients for inconsistent global degrees of freedom. Consider the two element matrices that are shown here for members A and B. The indices above and to the right of the matrices indicate which global degrees of freedom the stiffness coefficients correspond to. If we were to add these two stiffness matrices together directly, we would be adding stiffness coefficients that correspond to degrees of freedom 3 and 4 in matrix A to stiffness coefficients that correspond to global degrees of freedom 5 and 6 in matrix B. If we bring back this slide from our presentation on truss element stiffness, we can see that element A connects global degrees of freedom 1 and 2 with global degrees of freedom 3 and 4. However, member B connects global degrees of freedom 1 and 2 with global degrees of freedom 5 and 6. So simply adding the element stiffness matrices for member A and member B would be inappropriate from a structural point of view. Before we can add the element stiffness matrices together to form the global or structure stiffness matrix, each of the element stiffness matrices has to be expanded to include all of the degrees of freedom for the structure. You can see here that the 4x4 element stiffness matrix for member A has been expanded to include degrees of freedom 5, 6, 7, 8, 9, and 10, which are not directly associated with member A. And on this slide, you can see that the element stiffness matrix for member B has been expanded to include degrees of freedom 3, 4, 7, 8, 9, and 10, which are not directly associated with member B. I refer to these new matrices as the expanded element stiffness matrices. Each of them still includes their 16 original stiffness coefficients, but by expanding them from 4 rows and columns to a matrix that includes all structure degrees of freedom, we have prepared them to be added together to form the global or structure stiffness matrix. After all of the element stiffness matrices have been expanded, the last step in the process is to simply add the expanded element stiffness matrices together to form the global structure stiffness matrix. At this point, we can also assemble the load vector P. The load vector reflects the nodal loads that have been applied to the structure. For the truss that we have been considering, there is a 22 kip load applied vertically downward at node 3 that corresponds to global degree of freedom number 6. So the sixth element of the load vector is a value of -22. The negative sign indicates that the load is applied in the direction opposite of what we have defined as a positive displacement for degree of freedom number 6. Now that we have a global structure stiffness matrix assembled, there is one more step that needs to be completed before the system of equations can be solved for the nodal displacements. As it stands now, the global stiffness matrix K is singular and thus it can't be inverted. Mathematically speaking, we have a system of equations that are not linearly independent. The fact that the stiffness matrix in its present form is singular indicates that the model is structurally unstable. To remedy that structural instability, we need to modify the global stiffness matrix to reflect the fact that we have restraints on the structure. Once that is done, then the resulting global stiffness matrix will be a positive definite stiffness matrix. Unless you happen to have a minor in mathematics, you probably don't know offhand what a positive definite matrix is. So, naturally, let's go to Wikipedia for a definition. While this mathematical definition is quite specific, a common test is to make sure that the determinant of the global stiffness matrix is not zero. If there are zero or negative stiffness coefficients on the diagonal of the matrix, then this test will fail. However, simply observing that all diagonal coefficients are positive is not sufficient to guarantee that the matrix is positive definite. There are three basic approaches in the direct stiffness method to restrain the global stiffness matrix. That is, to reflect the physical supports of the actual structure on the global structure stiffness matrix. The first method is to delete the rows and columns of the stiffness matrix K, displacement vector delta, and load vector P that correspond to the restrained degrees of freedom in the structure. The second method is to add sufficiently large stiffnesses to the diagonal coefficients of the global stiffness matrix that correspond to the restrained degrees of freedom, such that the matrix becomes positive definite. And the third method is to reorder the rows and the columns of the stiffness matrix, the displacement vector, and the load vector, putting the free or unrestrained degrees of freedom first and the restrained degrees of freedom last. We'll talk about each one of these methods in the coming slides. Considering the truss that we've been using as an example, with the first method of restraining the global stiffness matrix, note that degrees of freedom 1, 2, and 10 are restrained. Degrees of freedom 1 and 2 are restrained at node 1 by a pin support, and degree of freedom 10 is restrained at node 5 by a roller support. To reflect those supports or restraints on the global stiffness matrix, we simply delete the rows and the columns that correspond to degrees of freedom 1, 2, and 10 from the stiffness matrix and from the externally applied load vector P. The stiffness matrix that results is referred to as the free global stiffness matrix, K sub FF. The first instance of the word free indicates that the rows remaining in the matrix correspond to free or unrestrained degrees of freedom, and the second instance of the word free indicates that the columns that remain in the matrix correspond to free or unrestrained degrees of freedom. We also delete the rows of the load vector P that correspond to the restrained degrees of freedom, resulting in the free load vector P sub F. At this point, we can invert the free global stiffness matrix K sub FF and then multiply the inverted matrix by the free load vector P sub F. When the inverted stiffness matrix is multiplied by the load vector, the result is a vector of displacements that correspond to the free degrees of freedom, delta sub F. A second method of restraining the global stiffness matrix is to add sufficiently large stiffnesses to the diagonal elements of K that correspond to the restrained degrees of freedom. For the truss that we've been examining, degrees of freedom 1, 2, and 10 are restrained. So in theory, these three diagonal stiffness coefficients should also reflect the stiffness of the supports of the structure. Recall that a stiffness coefficient, K sub ij, is the force corresponding to degree of freedom I that is required to cause a unit displacement corresponding to degree of freedom j, with all other displacements held at 0. Using the second method of restraining the global stiffness matrix, the expected support stiffness is added to these diagonal coefficients that correspond to the restrained degrees of freedom. In most cases, we would expect that the support stiffness would be infinite. In other words, the supports wouldn't move at all under any magnitude of force. However, adding infinity is problematic, so we typically add a value that is several orders of magnitude larger than the stiffness coefficients that are already there. Be careful though, if you add a number that is too large, it can create round-off error, though this is less likely to occur now with 64-bit operating systems than it used to be in the past with 32, 16, or 8-bit operating systems. When the inverted stiffness matrix is multiplied by the load vector, the result is a vector of displacements that correspond to the structure degrees of freedom. A test to determine if the values that were added to the diagonal elements of the stiffness matrix were large enough is to observe that the displacements corresponding to the restrained degrees of freedom are 0 or close enough to 0 to be satisfactory. A third method of restraining the global stiffness matrix is to reorder the degrees of freedom in the global stiffness matrix K, the displacement vector delta, and the load vector P such that the free or unrestrained degrees of freedom come first and the restrained degrees of freedom come last. If we do that, then we can rewrite the global stiffness matrix K as a matrix of matrices as is shown here. K sub FF, the free stiffness matrix, K sub FR, the free restrained stiffness matrix, K sub RF, the restrained free stiffness matrix, and K sub RR, the restrained stiffness matrix. Correspondingly, in reordering the degrees of freedom, the displacement vector delta and the load vector P can then be subdivided into delta sub F and delta sub R, which are the displacements of the free degrees of freedom and the displacements at the restrained degrees of freedom respectively, and P can be subdivided into P sub F and P sub R, which are the external loads that are applied to the free degrees of freedom and the external loads that are applied to the restrained degrees of freedom respectively. With this third approach, the system of equations goes from K times delta equals P to the expanded form that is shown here. If this is further expanded using matrix multiplication, then we develop two equations. One that results in K sub FF times delta sub F plus K sub FR times delta sub R equals P sub F. And a second equation that results in K sub RF times delta sub F plus K sub RR times delta sub R equals P sub R. It's still the displacements at the free degrees of freedom that we're after, so we can solve for delta sub F from the first equation, and we get delta sub F equals the inverse of K sub FF times the quantity P sub F minus K sub FR times delta R. And then if we have a situation where the supports of the structure don't move, i.e. there is no support settlement or anything like that, then the equation is simplified to delta sub F is equal to the inverse of K sub FF times P sub F. Again, consider the unrestrained global stiffness matrix for the example truss, and reorder the rows and columns of the stiffness matrix, placing the free degrees of freedom first and the restrained degrees of freedom last. Then we end up with the reordered global stiffness matrix shown at the bottom of this slide. Then we can identify the four sub-stiffness matrices K sub FF, K sub FR, K sub RF, and K sub RR. The same process is applied to the displacement vector delta and the load vector P, as is shown here. At this point, we can invert the free stiffness matrix and multiply it by the load matrix and get the free displacements for the structure. Taking another look at this slide, the vector P sub R can represent two different things. In one context, it's the vector of external loads that are applied directly to the restrained degrees of freedom, but in another context, it also represents a vector of reaction forces corresponding to the supports of the structure. If we solve for the reactions, we could find that they are equal to K sub RF times delta F plus K sub RR times delta R. However, R net in this equation is the vector of reactions due only to the loads that were applied to the free degrees of freedom, and it does not include any loads that may have been applied directly to the restrained degrees of freedom. In order to get to total reactions, we have to account for external loads that are applied directly to the restrained degrees of freedom, so thus we take R total equal to R net minus P sub R. In summary, we have three methods to restrain the global stiffness matrix. The first method is simply to delete the rows and columns. The second method is to add sufficiently large stiffnesses to the global stiffness matrix. And the third is to reorder and partition the stiffness matrices as part of the solution process. The first method is arguably the simplest, but offers the least amount of flexibility. The second method is effective, but requires some judgment in determining what constitutes a sufficiently large stiffness value to add to the coefficients. While the third method is more complex than the others, it offers advantages that the first two methods don't. Using the third method, we can solve directly for reaction forces, and we can incorporate support settlements and displacements at restrained degrees of freedom into our analyses that can't be accounted for using the other two methods. To close, let's summarize the direct stiffness method as we know it so far. The first step is to identify and label degrees of freedom at each node. Then we formulate the member stiffness matrices K sub I. Next, we expand the member stiffness matrices to include all of the structure degrees of freedom. Then we assemble the global stiffness matrix K. Next, we assemble the load matrix P. Then we reorder the global stiffness matrix K and the nodal load matrix P, putting the unrestrained or free degrees of freedom first and the restrained degrees of freedom last. Then we solve for the displacements, delta sub F, at the free degrees of freedom. And then in step 8, we solve for the structure reactions. In step 9, we back multiply the member stiffness matrices to find the member end actions F sub I. This was covered in the first presentation. And then as the last step, we solve for the internal member forces as needed.